Hello students, this is Professor July, and in this video we're going to briefly go over the Born-Haber cycle. Now in the Born-Haber cycle, typically we want to figure out what the lattice enthalpy is, right? And we talked about lattice enthalpy in the previous chapter, where we take the ions of the two compounds, typically in the gas state, and then we're trying to form the solid crystal. And so when we do that, we release the energy. So just to point out how this graph is written, as we go up on this graph, we have increasing energy, and as we go down, we're releasing energy. So to form that, we release energy, and we said how that energy or enthalpy is the lattice enthalpy. But finding out what that is from experiments is not as straightforward as you might think. Like, how do we get gas phase cations and anions to begin with to figure out the lattice enthalpy? What we can figure out is the enthalpy of formation, right, starting with solid cesium and gaseous, in this example, fluorine, right? These are the elements in their standard states at in their standard states, right? So cesium is a metal, exists as a solid. Fluorine exists as a gas, F2. And so we could figure out their standard enthalpy of formation, and we will get a number. How does that help us to figure out the lattice enthalpy? Well, there's a whole series of process that we could do to figure out the lattice enthalpy, and it's based off of the Hess's law that we studied a few chapters ago. So let's look at this. Okay, so our aim here is to figure out this transition going from these guys to cesium fluoride, right? But we can't figure that out. So why not, instead of going from this step straight to that step, we use Hess's law and go a longer route. Let's say we go this route. I'm going to use a highlighter, maybe that'll make it easier. We go this route, then down here, and then down here. Again, we know this is the enthalpy of formation. All right, so those are two ways to get from the same starting point to the same ending point, which is what we're interested in. All right, so let's do that. So instead of going from here, what we've done is we've gone from a fluorine gas atom to a fluorine ion. So if we go backwards, will be the opposite of this, right? We're going up in energy. So let me just write that again to make sure that we understand what's going on. The forward reaction here, right? We're going from a fluorine gas to fluorine ion. So we're going from fluorine gas, single atom, to a fluoride ion in the gas molecule. So to do that, we had to add an electron. And the enthalpy for this reaction, right? We know what this is. You add an electron to something, that's the electron affinity. So if we're going backwards, right, we're starting with fluoride ion, and we're going to fluorine gas atom plus an electron. And so what we'll have here is the negative electron affinity. All right, now we're going backwards, right? So in this step, we went from a fluorine gas atom to half of a fluorine gas molecule. So we took the forward step right here was we take half of a fluorine molecule and we break it apart into one fluorine atom. So the reverse then would be we have a fluorine gas atom and we form half of a fluorine gas molecule, right? Here, the energy there is a dissociation energy, the energy to split apart an atom, but we want negative the dissociation energy. Okay, let's look at the next step. In this forward step, we went from cesium gas atoms to cesium gas ions. So the reverse step is going to be going from ions to gas atoms. And we know when we went from a neutral compound to a positive compound, that energy is called the ionization energy. Remember, ionization is the energy it takes to remove an electron. So to go backwards, we started with a cesium plus in the gas phase. We add an electron to form a cesium in the gas phase. And so this will be negative the ionization energy. All right, let's go one more step now. In this step, we went from cesium in the gas phase to cesium in the solid phase. Going from solid to gas, that's sublimation. You add some energy. So let's go backwards. We go backwards from cesium in the gas phase to cesium in the solid phase, and this is going to be negative the enthalpy of sublimation. That's why we have a little s there. Okay, and then here, right, still we're trying to get there, so we need to account for the enthalpy of formation. So in the enthalpy of formation, we start with a cesium. Let me just erase some of these so we can see what we're dealing with. Cesium solid and half of a fluorine gas, and we're going to the product that we're interested in. So we start with cesium solid plus half of a fluorine gas to form our cesium fluoride solid. And this is the enthalpy of formation, and we don't have to put negative because this is the direction that that reaction wants to go in. So that is the enthalpy of formation. All of these are in standard states. That's why we see the little, where are we? The little zero right there. I've just ignored all of them in this equation, but we could easily add them. Whoops, there. There we go. Okay, let's see if all of these add up to what we wanted, which was the lattice enthalpy, which is going from the ions to the solid. How do we figure that out? Well, let's add everything. On the left, you have F minus gas plus F gas plus cesium plus, which is gas, plus the electron, never forget the electron, plus another cesium gas atom, plus a cesium solid, plus half of a fluorine gas molecule. And on the right hand side, we have fluorine gas plus an electron plus half of a F2 gas plus a cesium gas atom plus a cesium solid atom plus a cesium fluoride solid. All right, let's see what all cancels out. I see a fluorine gas here. I see an electron there. Here's half a fluorine gas there and there. Here's a cesium gas. There's a cesium gas. Here's a cesium solid. There's a cesium solid. So what we're left with is a fluoride gas ion, cesium gas ion to form cesium fluoride, which is exactly what we wanted. Fluoride gas plus cesium plus gas to give us our cesium fluoride in a solid form. And so if we add up all of these different enthalpies, we should get the lattice enthalpy. Now, whenever you have a cycle like this, a Born-Haber cycle, you can figure out any energy here if you know all the other energies, right? You just need to figure out what direction you want to go in to write the different equations and have the different signs and the different lattice enthalpies to form the one that you didn't have, the one that you're missing. All right, so that's a brief, hopefully it was a brief description of what the Born-Haber cycle is. It's just this cycle to help us figure out any of the different missing energies. Typically it's a lattice enthalpy, but we can use it to figure out any of the other missing enthalpies in this this reaction cycle. All right, that'll bring us to the end of this video. In our next video, we're going to look at molecular structure and polarity. I'll see you then. Bye.